In question 1 here of section A, as always, this is the experimental section. So question 1, I think 1 to 3 normally is the experimental questions. And in this instance, question 1 is always a question on titration. So there's loads of titrations on the course and they can kind of ask any of them. So luckily enough, most of them are quite similar. But in this case, this is one asking us about bleach and hypochlorite as well, which is a component of bleach. In the question, we were told just a little bit of kind of how the solution was prepared. So we were told that we were asked to determine, or in order to determine the hypochlorite concentration in some bleach, they took these steps, and we're also given a few formulas here. So here we can see the first one down here, and we also have this one further down, and these two can come in kind of handy later on for the maths portion of the titration question. And luckily with these types of titration questions, the first few parts are always more theory based, and they're very easy to pick up marks if you kind of know them, and a lot of them are quite similar. All the titration questions theory can be quite similar, so it's not too bad. And the tricky part I always found was the math section. So yeah, let's get straight into part I. In part A here, we are asked to describe how the 25 centimeter cube sample of the original bleach solution provided in a beaker was diluted to exactly 500 centimeters cubed. So this is just a straightforward theory question. Part A tends to be, especially on these titration questions, part A tends to be one where they ask you kind of how to make up the solution, what's kind of the method behind it, and thankfully a lot of them are quite similar. So in this case it's just simple dilution, so the method behind this is kind of exactly the same for a lot of the other titrations. So once you learn it once and you know it well, it's good because it can come up, and this question here is worth 9 marks, so it's an easy 9 marks to pick. So here is the correct method you want to follow to successfully, or should I say correctly, dilute our sample of bleach, and it goes as follows. The first thing you want to do is use a funnel to transfer the original bleach solution into a prepared 500 centimeter cube volumetric flask. Now, important thing to know here is when it says prepared, it means it's been washed out already with deionized water, and it's just kind of ready to be used after following correct lab procedure. The second part of this answer is that you need to rinse the beaker. Funnel and glass rod into the flask using deionized water. Now, deionized water here is extremely important. It is one of those buzzwords that you see in this type of question, and it just makes sure that all of the rinsings are successfully transferred from beaker, the funnel, and the glass rod that you use to stir or transferring, and it just means that there's nothing kind of left behind, so that you get everything that you need. The third part of this answer is that you want to make up the flask with the bottom of the meniscus aligning with the mark on the flask, and finally you want to stopper and invert the flask several times. So basically this last one is basically saying that when you're filling it up, you need to make sure that the bottom of the meniscus inside of the flask lines up perfectly with the mark along the neck of the flask, so there'll be a mark on it saying, you know, at this point there's 500 centimeters cubed of fluid inside of it. So you want to make sure that the bottom of the meniscus perfectly lines up with that, and then the last line here is just saying that you want to put a stopper on it and invert it several times just to homogenize and mix the contents of the flask. This question was worth a total of 9 marks, and the breakdown goes as follows. This first line, you got 3 marks for writing it down, making sure to say that you use a funnel to transfer the original bleach into a correctly prepared 500 centimeters cube volumetric flask. So it's important that you mention you're using a funnel to transfer it into a prepared flask. And then the next 2 points, you could pick a few here. You can say a couple different things, but these are just the ones that I always remember. They're always the ones that come easiest to me. So you got 3 marks for saying that you need to rinse the beaker and rinse the beaker, funnel and glass rod into the volumetric flask, making sure to use the deionized water, and as well as that, you can also say that you want to make up the flask to the bottom of the meniscus with the aligned mark on the flask, and stopper invert it as well, and you got 3 marks for that as well. So I always write down maybe a few more points than you actually need, that's just kind of, I just learned off kind of a paragraph that you'd always say for these types of things, and it just means that if I forget something, I always have a few other points. So this is kind of how I do it, but in this case you don't need just as much information, you need this first point up here, you need this to get 3 marks, but the second 2 points, as long as you get any 2 of those, you are completely fine. In part B, we are asked, why must excess potassium iodide here, so Ki, be added to the dilute bleach solution? So this is actually one of the more difficult or tricky parts, I remember, of this experiment. When I was studying it, I always found this a little bit different, or should I say a little bit difficult to understand, but it actually boils down to a fairly simple explanation. So the correct answer to this question is that excess potassium iodide, or Ki, is added to ensure that all of the hypochlorite reacts to make sure iodide remains in solution. So remains in solution is also important there. So basically what happens in this reaction is when you're mixing, well, should I say, the reasons you're adding this extra potassium iodide is that this titration involves the use of iodine in several compounds, and if you do not add excess of this potassium iodide, what happens is the iodine itself will precipitate out of solution. And what we know about iodine already is that it is a kind of like a darkish color, kind of dark red. And in order for us to kind of perfectly do this titration, if the entire sample suddenly goes dark red, you won't be able to see the color change and stuff like that. So in this case, the reason that we add extra is to make sure that this hypochlorite reacts and keeps this in solution, meaning that like the color change isn't ruined by the whole thing suddenly becoming a dark red. The breakdown of the marks in this question is where there was just 6 marks going kind of just on their own, and you got the 6 marks for saying that all of the hypochlorite needs to react. So this was the 6 marks, and kind of just like adding on a wee bit more to say that the iodine remains in solution, and that was, as I was just saying, to make sure that the whole solution doesn't turn this dark red, and that would kind of ruin the titration because you wouldn't be able to see, the color changes when you add your indicator and stuff later on. In part C, we were asked kind of a nice handy one, and it's saying that we need to state the color change observed in the flask as a result of this first reaction. So this is kind of a unique titration because there's several color changes, not just kind of like the normal kind of just from one color to another. In this case, there's actually several. So when it says we want to find the color change of the first reaction, you kind of need to think of like, what's the first color change that happens when you're doing this experiment? The answer to this kind of goes as follows. It's just kind of a straightforward kind of color change, and it goes that the change is from a colorless color to a brown. So a key thing to note here is that we don't want to hear, and we never want to hear in chemistry this word clear, and clear is not something that we want. People can tend to use it quite a lot when they're thinking of colorless. Colorless is the correct word, and you actually don't get any marks at all if you say clear, so it's very important that you don't use it. But in this case, the color change that happens is from this color, or should I say colorless color, to a brown. And there's a little bit of variety in what you can say. You can say kind of a golden brown or a yellow brown or maybe even an orange, but as long as you're saying color in and around brown, you're fine. So this was a nice, simple, kind of straightforward question, just a really nice color change. And there was 6 marks going in total for it, and the breakdown was fairly simple. You got 3 marks for saying that it was colorless to start with, and you got 3 marks for saying that it changes into a brown, or as I was saying, you could say orange, or like a dark kind of reddy brown kind of type of thing. In part D, here we are asked kind of 2 sub questions. So in this case, we were asked in part I to identify a suitable indicator for use in the titration phase, or should I say the titration stage of this analysis. And in part 2, we were also asked, using this indicator, what is this final color that is observed in the conical flask at our endpoint? So these are 2, yet again, nice short questions kind of asking about our indicator and our color change. So as always with these types of titration questions, the first question tends to be how to prepare something in the experiment, a piece of apparatus, or kind of making up a solution. And there always is a question on the color changes that occur, and there tends to be also one that asks you what's the indicator, and sometimes they might even ask you why, but in this case we're just asked to identify a suitable indicator for this experiment. So here we have our 2 answers. For part I, the correct suitable indicator that we want to use here is starch indicator, or starch solution also works. And for part 2, the final color change that happens in this titration is that you see a change from this straw yellow to a kind of blue black, and then eventually and finally, should I say, to this colorless as well. So in this case, there was a little bit more of a complex kind of color changing pattern And this is kind of one of those experiments, I don't think there's many of them on the course, where there's actually multiple color changes in it, and there tends to normally just be like from kind of colorless to pink or something like that. So in this case, this is just a little bit more complicated to remember. So here you might notice that I use the words straw yellow. So that isn't actually like necessary. You can also use pale yellow, but I always find it easier to use kind of like a physical thing to help make the description a little bit easier to remember. So straw yellow, or if you do biology, you might say brick red sometimes, and that's kind of just makes it a little bit easier for me to remember. So that's why I've said straw yellow here. And yeah, bluey black, you can just say black or blue, that also works. But yeah, the breakdown of marks for this question was fairly simple as well. There was 9 marks in total going, and the breakdown was as follows. There was 3 marks for correctly getting the indicator right. So in this case, it was starch indicator or starch solution. And you also got 6 marks for this part 2, and the breakdown was 3 marks for each of the correct colours. So the important colours here were this bluey black to this colourless. Now, important thing to know here, you actually don't really need the original colour, the straw yellow, but just to kind of give you guys a kind of more perfect picture of what's actually happening during the reaction. It goes from the straw yellow to bluey black and to colourless. The reason you only need the last 2 is that you might, if you go back to the start of the here, it's asking us for this endpoint. Kind of like basically asking us like what's the color it changes from to get to this last color. So the last 2 colors involved would be this blue black and our colorless. So yeah, making sure as well to not say clear for colorless. Colorless is different, and it is super important that you remember it, because I've lost marks in the past to it myself, and I don't want anyone else to if they can avoid it. In part E, we are now moving on to what was my least favourite part of these titration questions, which was the maths. Sometimes it's very easy to go wrong with these types of things, but hopefully we're just going to take it nice and handy and go through these bit by bit. So part I tends to be one of the easier ones, and they can get a little bit more complicated as you go down. But yeah, let's just get straight into part I. So in part I, and especially in this kind of math section, you get given a lot of figures. So in this case, we are told on average 21.4 centimeters cubed of the 0.09 molar sodium thiosulfate solution were needed to proceed with this reaction in the conical flask once mixed with this 25 centimeter cube portion of our diluted bleach. So important thing to know here is this diluted bleach. And in part I, we are asked to find the average number of moles of the sodium thiosulfate used up in one of the solutions. So obviously, as always with maths in general, there's a couple different ways you can approach this, but I always kind of approach it using the same method each time. And in this case, it involves using a very important part of chemistry, especially in the calculations part, which is one of our calculation triangles. So one of the important triangles that I always use in chemistry and calculations is our moles, volume, and molarity triangle. So on the top here, we're going to have our number of moles. On the bottom half of our triangle, we're then going to have our volume, which is just going to be VOL, and then we're also going to have our concentration, which I'm just going to write as conc, just for short. So this kind of works the same as your DST triangle you might use in junior cert, which is like your distance, speed, time triangle. And this is exactly the same. So if you want to find your number of moles, you can multiply the volume and the concentration. If you want to find the amount of concentration and you know your moles and your volume, then you just divide the number of moles by the volume, and vice versa to find kind of anything you're looking for in the triangle. So in the question, we are told a few pieces of information. We are told that we need 21.4 centimeters cubed of this 0.09 molar solution in order to completely reduce the portion in our conical flask of the diluted bleach. And in the question, we're asked to find the average number of moles of this sodium thiosulfate solution. So we don't really care about the diluted bleach, because in the question, we're just kind of asked about this sodium thiosulfate. So it means we can actually use our triangle here to begin to find what we're looking for. So in the question, we were asked to find our number of moles. And that means that one thing we don't have is the number of moles. That's what we're trying to find out. However, what we are actually told is we're told our volume here. So this is a volume. And we're also told our concentration, or our conc, here as well. So what we're looking for is the number of moles, but we are actually told our volume and our concentration. What that means is that we can actually multiply the two of these together by looking at our triangle here. You can cover the one that we don't have, and you can see that in order to find the number of moles, we need to multiply our volume and our concentration together, and that should give us our answer. So writing this out, we're going to multiply our volume and our concentration. So our volume is going to be 21.4, and an important thing to note here is that when you're doing this volume has to be measured in litres. So there's 1,000 centimetres cubed in a litre, so it means that whenever we're working with this volume, we want to make sure that it is in litres. So to convert our centimetres cubed into litres, we're going to divide by 1,000, and that's our volume, and then we're going to multiply this by our concentration, so 0.09 moles, and then all we have to do is put this into our calculator to get the average number of moles of our sodium thiosulfate. So here I have my calculator. I'm just going to kind of plug in what we have so far. So in brackets, we're going to have our 21.4, and on the bottom we're going to have our 1,000, and yet again the reason for that is just that we need to convert our volume here to litres, not centimetres cubed. We want it in litres, so to convert centimetres cubed to litres we need to divide by 1,000, and then we're going to multiply this by our concentration, which is 0.09 moles, and we hit our equals, and that gives us in decimals, so change that, and we're going to get 1.96 by 10 to the minus 3 moles. Now obviously you can write this in scientific notation like it is here, or you can expand it out if you'd like to, but it doesn't really matter, so I'm just going to write it down in an expanded form. Writing it down here, we're going to have 0.001926 moles, and that is our final answer. So in this case, it was actually really simple once you kind of broke the question down, saw what we were given, saw what we were being asked, and used, in this case, one of the most important parts of volumetric analysis, this moles, volume, and concentration triangle, and it actually makes the question much easier, and I wish I knew about it earlier than I did, but yeah, I hope that was helpful. The breakdown of marks goes as follows. So just for part I, there was 3 marks going, and the breakdown was, it's really simple. The breakdown was just that you get 3 marks for getting your correct answer here, so that is the correct answer. In part 2, we are asked to find the number of moles of iodine reduced in each titration. So this is kind of yet again another just volumetric analysis question, but this one is actually much simpler. Once you kind of get the hang of them, they can come up quite often, but once you begin to see them and once you kind of done a few, it's actually really easy because it is literally just like a one-liner in terms of maths. But yeah, let's get straight into it. If we recall from our previous answer to the last question, we found out that the number of average moles, should I say the average number of moles of sodium thiosulfate needed to reduce the diluted bleach was 0.001926, and this was the number of moles needed. Now you might ask, how does this relate to the question we're asked above? We were asked the number of moles of iodine actually reduced, and the way that they're related is actually by using the formula that is given to us at the start of the question. So going back to the question we were given at the start, we're actually given these two formulas, which I've already drawn a little arrow beside, but the one that we're going to look at is this bottom one. And the reason that we're going to look about this bottom one is because the question we're asked is to find the number of moles of iodine actually reduced. So iodine, just right over here on the side, iodine is found in the form I2, so it's just a diatomic element. It needs to exist in a pair, and in this case we were already solved in part I of the math section and the average number of moles in the thiosulfates. We need to find the number of iodine that was actually reduced. If we look at this formula that I've underlined, we're looking for the number of moles of this I2, but what we actually found is the number of moles of this thiosulfate, which is actually this underlined section here in this kind of purpley color. So what we've actually done is we've already found the number of moles of this thiosulfate, and this formula actually relates the two of them together. So what we can see from this is that in front of both of these, there's actually two numbers. In front of the thiosulfate, we have this number 2, and in front of the I2, there's actually just a number 1. And you tend not to write it if it's just a number 1, but there is a number 1 there. And that kind of 1 to 2 ratio actually allows us to relate the number of moles of the thiosulfate, which we found in part I, to the number of moles of the iodine, which we're being asked for in part 2. So going back to my question here, what I just said was that by looking at that formula, we can actually see there is a relationship between them. The relationship goes as follows. So the amount of this thiosulfate that we found in part 1, which is represented as the formula S2, O3, and then there's 2 minus, and the ratio of that to the amount of iodine is actually a 2:1 ratio. So we already know half of this. We already know the amount of moles in this piece here. So if this is the 2 on this side, then if we want to find the 1, all we have to do is divide the number we found before by 2. Writing that down here, we can just say that looking at the number we found before, which is 0.001926, and we want to divide that by 2, we'll be able to find the number of moles of iodine that were actually reduced on their own. And the way we found that yet again is just by looking at the simple ratio that was given to us in the formula. I remember when I was solving these back kind of at the start of chemistry, kind of preparing for my own leaving cert, I was trying all these crazy different approaches, but the answer is actually really simple when you just understand how the formulas kind of relate the reaction together. So in this case, this 2:1 ratio is all that you need to know in order to do the maths here. So pulling open my calculator here, all I'm going to do is kind of fill in what we know. So as we said, 0.001926, this is the number of moles we found in part I. I'm going to divide that by 2 because it is present in a 2:1 ratio, and that means if we want to find the amount of iodine, we need to divide by 2. So putting that into our calculator, we're going to get 9.63 by 10 to the minus 4, and that's the number of moles of iodine reduced in each titration. As always, you can leave this in the scientific kind of notation form. Doesn't really matter, or you can write it out like kind of full. I'm going to do that just for my own peace of mind, but either way, it doesn't really matter how you write it. The answer that we got there was 0.000963, and this is the number of moles of iodine reduced. So the breakdown of marks for this question was as follows. Yet again, it was just a simple kind of maths question, so there's only 3 marks going for it, and you got your 3 marks for correctly getting this answer at the end. But the key observation here was realizing how the number of moles of iodine reduced relates to this number that we found in part I, the number of moles of the sodium thiosulfate. And by using our formula in it, we're actually already given this ratio. So it meant actually that if you have done this question before, and you'll see that it comes up quite often, it's actually really simple to make that connection. And you can kind of use this in lots of different titration questions because it kind of comes up all the time. So yeah, let's get into part 3. In part 3 here, we're asked to calculate the molarity of the original bleach solution, or should I say the original bleach, in terms of our hypochlorite ion. So the important things here to take away is that we are being asked about our original bleach solution, so try not to get that mixed up with our diluted one. And another thing here is if you don't understand what molarity is, it's just another way of saying our concentration. So if it's just easier for you to understand concentration instead of molarity, I always used to write down concentration wherever I saw molarity because sometimes I get them mixed up. So in this case, if that just makes it a bit easier for you, of course, write that down. So this question is asking us to find the concentration of the original bleach in terms of our hypochlorite ion. And in this case, we're going to go back to our question to look at our formulas and see if there's any other relationships that we can find. So coming back to our question at hand, we actually are going to use this formula up top here to see our relationship that we're going to use for this question. So what we can see here is that there is for every one chloride ion, so this Cl O- is our chloride ion, we have 2 of these I- ions as well. And basically it means that that ratio is constant, and it's, you know, just kind of something that we're given in our question. Another thing to note is that we were also in the last question, we found the amount of moles in our reduced, or should I say the amount of iodine reduced in each titration sample. So we found the amount of moles of this I2 down the bottom. Now the reason that that might be important, and you might be able to understand it kind of right now, but the reason it is important is because the amount of iodine atoms actually down here at the bottom, if you look, there's 2 down here, so there's just 2 in this section, and also up the top here there is 2 of the I minuses, so it means that the ratio between the 2 of those is constant. And that's kind of the key principle that this titration works off of, because there is the same amount of iodines present in the reaction, or in both formulas should I say, it means that we can actually build a much bigger relationship between them all instead of having these 2 separate formulas. And it means that we can look at this as a bigger relationship overall. The relationship that we can actually look at here is the Cl O- ratio to our 2I- is the same as our Cl O- is to I2. So just to kind of put that in a wee bit of a box here, this is the same relationship, and the reason it is the same relationship is because the number of I2s present is the same in both, and it means that we can actually relate the two of them directly together. The reason this is important is because in the last question we found the concentration of our iodine, so this I2 over here, and it means that because the two of them are now related to each other, and we have this kind of formula in our box here, it means that we can actually find the amount of this ClO- or hypochlorite ion, which is actually what we're being asked for in our question. Going back to our question here, we're going to write down just kind of everything that we found on the question sheet. So what we said was our ClO- or our hypochlorite ion is the ratio that has to our 2I- is exactly the same as the relationship between our hypochlorite ion and our I2. And the reason that's important is because we already know the concentration of this I2, which means that we can use that to find the concentration of our hypochlorite ion. If we look back into the previous question, we know that our concentration of our I2 was going to be 0.000963 moles of I2, and therefore that means that there's going to also be 0.000963 moles of ClO-, which is our hypochlorite ion. In the question, we were asked to find the molarity of the original bleach in terms of hypochlorite ion. So what we have done now is we have found the number of moles of the hypochlorite ion present in our diluted bleach, and because as we know in the question we are told that this reaction is all done with bleach that has been made up and diluted into a solution. So we know now the amount of moles in our diluted bleach, so we need to convert that to the amount of moles in our original bleach. First thing to note here is that in the question we were asked for our molarity, and so far we have been able to find the number of moles in our ClO-, our hypochlorite ion. That means that we need to convert our number of moles into a molarity, and using our triangle that we found before, because we know the number of moles and we're looking for our concentration or molarity, it means that we can cover our concentration or molarity, and it means that we need to divide by our volume. So in order to convert this into our molarity, it means that we have to divide by our volume. So we're going to divide our 0.000963 moles, and we're going to divide this by the volume associated with this, which was 25 centimeters cubed. But an important thing to know here is that we want to have this in liters as always when we're dealing with volume. So we're going to divide this here itself by 100 centimeters cubed, and that 100 centimeters cubed is going to just convert that 25 centimeters cubed into liters. So once we plug this into our calculator, we're going to be able to get our molarity of our diluted bleach. So pulling up our calculator here, we're going to have our 0.000963, which is going to be our number of moles, and then we're going to divide this by our volume, which we said that there is 25 centimeters cubed, but to convert this into liters, we're going to need to divide that itself by 1,000. So as always, converting from centimeters cubed to liters is you need to divide by 1,000. So that's where we're dividing by 1,000 here, and plugging that into our calculator, we're going to get 0.03852, and that's going to be the molarity of our diluted bleach. So writing that out, we're going to have our molarity to be 0.03852, and this is going to be in molar. So important thing to note here is that this is going to be our diluted sample. So now that we know the molarity of our diluted bleach solution, it's actually fairly easy to convert this into our original bleach solution and find the molarity of that. And all we have to do now is multiply by our dilution factor. This is just a wee side note on what a dilution factor is. A dilution factor is just kind of how we're able to relate a diluted solution and a original solution. So in this case, we want to relate our diluted bleach to our original bleach, and the way that we do that is using this dilution factor. And the dilution factor is just a number, and you can find it fairly easily. In this case, it's by looking at what we're told at the start of the question. So at the start of the question, we were told that we had an original solution of bleach which was 25 centimeters cubed, and this was converted using a method to a diluted sample which was now 500 centimeters cubed. So it means that it was diluted from 25 centimeters cubed to 500 centimeters cubed. So in order to find our dilution factor, all we need to do is divide our 500 centimeters cubed by the original amount. So it's going to be 25 centimeters cubed. And if you want to plug that into your calculator, you'll see, well, first thing to know here is to see that our units are going to cancel. So that means it's just going to be a number. And 500 divided by 25 is going to be a factor of 20. So it basically means for every one, basically means that 25 centimeters cubed of original bleach was expanded way out into this 500 centimeters cubed. So the ratio there was 1:20. So we need to use this dilution factor of 20 in order to find our original bleach molarity. Now going back to our question, what we have is the molarity of our diluted solution, which was 0.03852 molar, and then we're going to multiply that by our dilution factor, which we found earlier, which was going to be 20 in this case, and that's going to give us our molarity of the original solution, which is what the question has asked. Pulling up our calculator here, we have already got our answer from before, so I'm just going to multiply this by 20, and it means that our final answer is going to be 0.7704 molar. So that's just going to be the molarity of our original bleach solution. I'm just going to write in here original, just so I don't get myself mixed up if I ever need to use this later on. And the reason I've wrote in diluted and original here is just sometimes I myself can get confused with which number represents what, and just kind of writing out makes it a little bit easier if I need to look back and make corrections, or if I'm kind of looking over my work towards the end of the paper. The breakdown in marks for this part of the question was fairly simple as well. There was a total of 6 marks going, and the breakdown goes as follows. You got 3 marks for correctly kind of understanding the relationship between the hypochlorite ions and the 2 I- ions, and how that kind of relates to what we found earlier, and the I2 or iodine. Another important thing in order to get those first 3 marks was actually finding the molarity in the diluted bleach, which would be this line here. So the way we found that in this case was dividing by our volume, because as we know, using our triangle that we discussed earlier, if you want to convert a moles to a concentration, you divide by a volume. In this case, the amount of volume associated with this was the 25 centimeter cube portions in the conical flask, or should I say in the beaker, and you need to make sure that's in liters, so we had to divide by 1,000, so that's where we're getting that 1,000 from. Finally, you're getting your last 3 marks for your final answer, which was the molarity of our original solution, and the key thing you needed to do there was multiply by our dilution factor, which kind of discussed earlier, and the process for finding that is the same for different questions. That's how you get your total marks for that question. In part 4 here, we are asked to calculate the concentration of the ClO- ion in the original bleach, so making sure to work with the original bleach here, not the diluted one, to the nearest whole number expressed as a percentage weight per volume. First thing to know here is that we are asked for concentration, but instead of having it in moles per liter or in molar like we've already done, we're asked for something as a percentage weight per volume. So just to write a little kind of side note here, W divided by V in this case means weight per volume, and that means that we can go from our moles per liter, which we've already found, and change that hopefully into a weight per volume. Since originally we were working with moles per liter, and now we're looking for a weight per volume. Since liters are already a volume, we don't need to convert that. So yeah, now all we have to do is convert our moles into a weight or a mass. Because this question is asking about the concentration of the ClO- ion in the original bleach, we can actually use the answer we found in the previous question, because there we found the molarity of the original bleach as well. So we can actually use that information in this question. So if we recall back from the last question, the molarity of the solution was 0.7704 m, or molar. That's another way you can say that is 0.7704, and that would be moles per litre. Now what we have is moles per litre, and as we said earlier, we're looking for weight per volume, so we need to convert our moles to a weight or a mass in this case. And yet again, we're going to be using the other really important kind of volumetric analysis triangle here to convert from moles to mass. And yeah, it's very important, and I wish I spent more time kind of working with it and getting familiar with it, because it's such a lifesaver in these types of questions. So in here now we have our triangle. I'm now going to fill it out for our volumetric analysis in this case. So we're looking to convert between moles and mass, and yep, there's a separate triangle from the one that we looked at earlier, so I'm going to fill that out now. On the bottom of the triangle, we're going to have on the left moles, and as well as that, on the bottom we're also going to have so you might understand what RMM stands for. RMM stands for relative molecular mass. It is just kind of the mass of the atom that you'll find when you look on your periodic table. So when you're in your log tables in your exam, when you are flicking through them, you'll see the relative molecular mass of each of the atoms, and we're going to be using that in this question. At the top of our pyramid here, we're going to have our mass, and this kind of brings all of these key things together, because if we're looking for a mass, we can multiply the number of moles times the relative molecular mass of the molecule, or if we're looking for moles, for example, we can divide mass by relative molecular mass, and yeah, that should get us back to whatever you're looking for by using this really simple and very handy triangle. So we are looking for the concentration of ClO minus, and as we said earlier, that is weight per volume, which means we need to convert moles into mass. So in this case, using this triangle, if we want to find mass, the way we can do that is by covering mass on our triangle and seeing what's left. So when we cover mass on our triangle, we see that moles and relative molecular mass are left on the bottom, which means that in order to find our mass, we need to multiply the number of moles multiplied by relative molecular mass. Cool. Now we are already told, or should I say we already know the number of moles, because we're told that actually just here, the number of moles is 0.7704. So what we need to do now is actually find our relative molecular mass for this ClO minus ion. The way we do that is by going to our log tables and finding out all of the molecular, or should I say the relative molecular masses of the components of the ion and adding them together. But just to write it out, what we're going to have is the relative molecular mass of ClO minus is going to equal to all of the relative molecular masses of the components added together. To find these, they might be listed at the start of the paper. Sometimes at the start of the chemistry paper, they give you the more commonly used ones throughout the exam, and it means you don't have to use your log tables for this. But for this example, I'm going to go to my log tables and use the periodic table provided to us. So flicking to the back of our log tables, we should find our periodic table. So there's several different ones, and they kind of give you different pieces of information. One will tell you electronegativity values, others will tell you ionization energies, but in this case, we're just looking for our standard periodic table. As I was saying earlier, in order to find the total relative molecular mass of the ClO minus ion, we need to add together the relative molecular masses of its components. So in this case, the relative molecular components are Cl and oxygen, and in this case we only want one oxygen, so just make sure you don't add two together because you might be used to dealing with O2. It's just one oxygen in this case. Going to the table now, we're looking for chlorine, so chlorine is over here, and as we can see down the bottom here, our relative molecular mass is 35.45, so I'm going to round that just up to 35.5. You don't really lose marks if you are a little bit more accurate in this case, but rounding to the nearest decimal place tends to be completely fine, and they won't penalize you for that. The other thing we need to add here is oxygen, so if we look for oxygen, it's going to be up here. So oxygen is number 8, and its molecular mass, or relative molecular mass should I say, is 16. Adding the two of these together, we'd be able to get a total of 51.5, which you can of course verify with your calculator if you want to. I know if I was doing in my exam, I would just, because I've made enough mistakes doing simple addition like that, but in this case, adding 35.5 and 16 together will give us a total of 51.5. Going back to the question at hand here, because we have already written out, or should I say we've already found our relative molecular mass of ClO minus, and we know that to be 51.5, we have all of the components that we need in order to finish out this question. So as I was saying up in this line over here, in order to find our mass, we need to multiply the number of moles and the relative molecular mass. So I'm just going to do that down the bottom here. What we're going to have is 0.7704, and then we're going to multiply that by 51.5 to give us our mass. So here I'm going to grab my calculator and I'm just going to plug in what we have into the calculator. So it's going to be 0.7704 times 51.5, and it's going to give us a total of 39.6756. Now, as we were working with mass now, this is going to be grams, and an important thing to remember here at this time is that this is going to be per liter. The reason it's going to be per liter is because we have actually just converted mass, or should I say we've actually just converted moles to mass, which means that we haven't changed the concentration, we're just kind of writing it differently. So if we had moles per litre up the top here, it means at the bottom we're going to have mass per litre, and in this case mass is going to be measured in grams. We're almost finished the question here, but as we were saying earlier, we are looking to find it as weight per volume. Weight per volume, as we said earlier, is going to be different from the moles per litre, and we've made that conversion, but an important thing to note here is that weight per volume is actually going to be grams per 100 centimeters cubed. So what we have at the minute is we have grams per litre. There are 1,000 centimeters cubed in a litre, which means we need to convert that per litre into per 100 centimeters cubed. The way that we're going to do that is going to be dividing by 10, and I'm going to explain where that comes from now. We're we're going to take our 39.6756 grams, and then we need to divide by, it's going to be our 1000 centimeters cubed, or our liter, all divided by 100 centimeters cubed, and you're going to put some brackets around them. The reason that we're dividing by 1000 centimeters cubed divided by 100 is because we want to find out how many hundreds fit into that 1000 centimeters cubed. By dividing that just kind of offhandedly on your calculator, you'll find out that the answer is 10, and it means that basically there are 10 100 centimeter cubed portions inside of that liter. If we're looking for what 100 centimeters cubed has relative to what there is in a liter, then we need to divide that original number by 10. So in this case, we're going to be dividing that 39.6756 by 10. This is a very simple division. You don't need to really use your calculator. All it is moving the decimal place one spot to the left. So we're going to get 3.96756 grams. Writing this out now, we're going to be moving the decimal place one spot to the left because it's just dividing by 10. So our answer here is going to be 3.96756 grams per 100 centimeters cubed. Now, as I was saying earlier, we're looking for a percentage, and because this is in grams per 100 centimeters cubed, it's already in the correct format, and it said round to the nearest whole number, so we're going to be rounding that to 4. So it's just going to be 4%, and then weight per volume. The breakdown of marks for this question goes as follows. There was a grand total of 8 marks available. You got your first 3 marks for correctly identifying and using your volumetric analysis triangle, and then finding the relative molecular mass of the chloride ion. So in this case, that's where your first 3 marks come from. Your second 3 marks go to actually finding the mass per liter. So in this case, you get 3 marks for saying that the mass per liter of the solution was 39.6756 grams. And ultimately, you get your last 2 marks for getting your answer. So in this case, it's 4% weight per volume, and that's just because we're rounding to the nearest whole number, and that'll give you your total of 8 marks.